Okay, welcome everybody. Thank you so much for being here with us today. Today, we are very fortunate to have with us Professor Stefano Ermon. Stefano is an assistant professor of computer science in the computer science department at Stanford University, where he is affiliated with the Artificial Intelligence Laboratory and is a fellow of the Woods Institute for the Environment. Stefano's research is centered on techniques for probabilistic modeling of data and is motivated by applications in the emerging field of computational sustainability. He has won several awards, including 4 Best Paper Awards at AAAI, UAI, and CP, and NSF Career Award, ONR and AFOSR Young Investigator Awards, a Sony Faculty Innovation Award, a Hellman Faculty Fellowship, Microsoft Research Fellowship, Sloan Fellowship, and the HKI Computers and Thought Award. Stefano earned his PhD in computer science from Cornell University in 2015. On behalf of everybody here, thank you so much, Stefano, for making, taking time out of your busy schedule to be with us here and for agreeing to share your research with us. And we are very excited to hear what you have to say. And please feel free to get started whenever you're ready.
All right. Yeah. Thank you so much for the great introduction. And I'm excited to be here and tell you about some of the research we've been doing at Stanford on using AI to help address sustainability challenges. And yeah, I'm happy to take questions throughout the talk, so feel free to interrupt me or send a chat message, and yeah, don't be shy. So the setting, just to provide some background, is that, as you probably know, if you are following or you are in artificial intelligence, there's been really a lot of progress in the last few years. In computer vision, we've been able to build systems that are pretty good at interpreting images, detecting objects, classifying images, and they perform reasonably well comparably to humans on pretty challenging benchmarks like ImageNet. We've made a lot of progress on speech recognition, natural language processing, game playing, protein folding. The whole field of AI is booming, and it's pretty clear to me that these technologies are going to have a huge impact on pretty much every aspect of society and the economy. And given this transformative potential, kind of the research question that motivates a lot of my research is really thinking about how can we use these amazing technologies that we're developing to promote the well-being of humanity throughout the world, and which basically means how to make sure that these technologies are actually used to help out as many people as possible, right? How do we use them so that they don't further increase inequalities, but they actually end up benefiting people throughout the world. So in this context, I think a lot about issues of sustainable development. You see here the 17 Sustainable Development Goals from the UN. I think these are the big challenges that our society is facing today. And you can see problems like ending extreme poverty, fighting hunger, climate change, finding new sources of affordable and renewable energy. I think these are the big problems that our society is facing today. And what I'm excited about is thinking about ways in which I can use what I know, which is AI, ML, optimization, and think about ways I can help. How can I use all these technologies that we're developing to make progress toward these problems? And clearly these problems are hard and we're not going to solve them with an algorithm. But what I hope to convince you in this talk is that there are ways in which we can contribute as computer scientists. So specifically, one reason these problems are so hard is that we actually understand very little about what's going on, especially in the poorest part of the world. This is a quote from Kofi Annan that I think exemplifies this concept pretty well. This is from a recent Nature paper that he wrote in 2018. He says, data gaps undermine our ability to target resources, develop policies, and track accountability. Without good data, we're flying blind. If you can see it, you can solve it. Right. So it's one thing to say, okay, we want to end extreme poverty by 2030, but if you are not measuring how many poor people are there, where they live, whether interventions you're implementing are working or not, it's very hard to make progress toward these targets. And indeed, the situation is pretty bad on the ground. For example, if we look at extreme and at the SDG number 1, ending extreme poverty, the way we typically collect data on these kind of outcomes is through economic surveys, nationally representative economic surveys. And these surveys are expensive to conduct. And as a result, they are not done very frequently, either because of cost reasons or for political reasons. And so one thing that we did is we tried to actually quantitatively evaluate how much data is actually out there for different countries. And you can see on this map that here every country is color coded by the interval between surveys that we have. And you can see that in many countries you might need to wait many years, maybe a few decades between two consecutive surveys. There are countries in which there's no economic data available at all. And as a result, it's very hard to figure out if we're making progress. It's very hard to figure out if governments are doing what they are saying they're doing. Very hard to figure out whether interventions are working. Very hard to do social science research and figure out, you have two kinds of interventions that you could do. Which one should you implement? Very hard to answer these questions with this kind of economic data. And it's probably clear from the picture, but as you can see, the biggest data gaps are here, let's say in Africa and other developing countries. And indeed, if you try to regress the number of surveys that are available as a function of GDP per capita, you're going to see the kind of relationship that you would expect, where most of the data is available in relatively richer economies, and the poorer a country is, the less survey data is available. And similarly, there is some kind of negative correlation between the amount of data available and some index that is kind of basically measuring the level of political freedom in that country. So the less politically free a country is, the less survey data is available for that country. And this is not just for economic data. If we look at other key inputs for these SDG challenges, if we look at population data, we know the population is growing, but how much? Where do people live? Even that kind of information is relatively scarce, especially in certain parts of the world. So we did the same kind of analysis. You can see it here in the bottom plot, showing basically how much census data, population census data is available across different countries. And in many countries, that data is pretty scarce. It's definitely not as good as it should be. And if you look at agricultural censuses, which are kind of like key inputs as you're thinking about food security and hunger, again, the situation is there are huge data gaps. We really don't know what's going on the ground, especially in the poorest parts of the world. And so, given this background, we have these big problems that we all want to solve, but we have very little data to think about and to implement data-driven decision making. And so one of the questions I've been thinking about over the last few years is whether there are better ways to collect data on a global scale, and in particular, figure out alternatives that are more scalable than just sending people on the ground and knocking on doors to fill out surveys. And so we've been looking at ways to leverage data that is collected cheaply, passively, like from satellites, from phones, from crowdsourced, and it's globally available, it's cheap. And the idea of the research that I'm going to talk about in this talk is how can we take advantage of all of this data that is available and is relatively inexpensive, and can we combine this data with machine learning and advances that we've seen in computer vision and AI to essentially try to make sense of this data and come up with more scalable ways to infer economic indicators, figure out how the world is changing, how the environment is changing, and provide the data that we need to understand these big problems that we would like to address. So specifically, one key source of data that has gotten much better over the last few years is remote sensing data, so satellite images. There's been a lot of progress in the technology. There's been a lot of private companies that have entered the market. They're driving the cost down. They're improving the capabilities that we have. Maybe 10 years ago, the kind of images that were publicly available and researchers were working with were of 30-meter resolution. So every pixel basically corresponds to an area of 30 meters by 30 meters. And this data was hugely successful, hugely useful for a lot of different things, but the resolution is just not good enough to see what's going on the ground. Well, these days it's very easy to get access to much higher resolution images. Maybe you can basically get an image of the whole world at a 3-meter resolution. So every pixel corresponds to an area of 3 meters by 3 meters or even less. And these kind of images are updated every day. If you're willing to accept lower refresh rate, so you get images less frequently, you can get even higher resolution. You can go down to 1 meter or 0.3 meters, where you can start to see a lot about what's going on the ground. You can start to see cars, you can start to see buildings, you can start to see almost kind of containers, on a ship, on a shipping yard. So there is clearly a lot of information about economic activities, about where people live, about the economic conditions on the ground that is contained in these images. And the promise here is that perhaps there is a way to combine all this data with the advances that we've seen in AI and ML and computer vision to come up with scalable ways to understand what's going on the ground in a much more inexpensive way compared to sending people filling out surveys. So just again, to be a little bit more quantitative here, we did a recent study kind of like trying to get a sense of how good is the data that is available today. Let's say in a place like Africa, which is arguably one of the places where the quality of the data is worse. So this is kind of like a lower bound to what's possible in other parts of the world. And as you might expect, there is kind of like a trade-off between the spatial resolution of the images and how and the temporal resolution. So if you want higher resolution images, then you're going to get them less frequently. But if you're willing to accept lower resolution images, then you can get these images updated much more frequently, maybe every day. So this was the situation. There's kind of like a Pareto frontier here, looking at the spatial resolutions versus the temporal resolution, how frequently you're going to get the allocation basically is going to be revisited by the satellite. And the curve in blue is basically the Pareto frontier in 2010. And now if you look at the situation in 2020, you can see that the Pareto frontier has shifted quite a bit. And now it's possible to get relatively high resolution images like planet imagery, maybe let's say 3-meter resolution images, like you can see on the yellow or orange line, updated maybe every few days. And so this is really providing opportunities that were not possible before for coming up with new ways of sensing what's going on the ground. And in particular, we know that because surveys are expensive and they are done very, very infrequently, the kind of granularity that we get when we think about traditional surveys is very, very poor. Even when we do the surveys, we can only survey a tiny fraction of the population. And as a result, you can do this kind of like back of the envelope calculation, and you can check, okay, how frequently would a typical household, let's say in Africa, or a typical household in the US be surveyed using one of these traditional kind of sending people on the ground approaches. And you can see that the curve over time would look something like this in the US, it would look like something like this in Africa. And here, the idea is that in the US, a typical household would basically be surveyed every roughly 10 years, right? That's typically how frequently surveys are done in the US. In Africa, the situation is much worse. A typical household will be surveyed once every 1,000 years or more, which is a pretty horrible situation. On the other hand, if we look at how frequently a household is going to be viewed from space using one of these satellites, we see that there is a huge gap. A typical household in Africa might be visited, once a week, once a month, something like that. So if there is a way to somehow infer something interesting from the images we get from space, that might give us tremendous, like a completely transformative way of thinking about collecting economic data across the world in a much more scalable way. And so that's kind of like how we've been thinking about a lot of the projects that we've been working on, thinking about ways to essentially measure various kinds of economic indicators across the world using satellite images. As we've seen, satellite images are readily available. You can get them pretty much everywhere in the world. They are updated frequently. They contain a lot of information about what's going on the ground. And so we've been looking at ways to combine that with recent advances in machine learning and computer vision to see to what extent we can essentially make sense of these images automatically and infer useful indicators that would be typically acquired by basically sending people on the ground in a way that is, as we've seen, not scalable and that is creating these huge data gaps that are really hampering the progress towards the sustainable development goals. Now, this all seems great, but one challenge is that although we have a lot of images, as we've seen, there's a lot of satellite data that is becoming available everywhere. There's typically not a whole lot of training data that is available to just train a deep neural network end to end to predict what we care about from satellite images. And so a lot of the technical research on the AI and the ML side is how do we get around this data scarcity? How do we develop models that can predict these indicators that we care about, let's say poverty or food security or population density or access to infrastructure quality, and do that when we have access to a relatively small amount of training data. And so a lot of the techniques that we've been developing are, I think, can be broadly understood under the umbrella of weak supervision. So we've been developing techniques that essentially take advantage of the fact that we typically have access to different modalities. Maybe we don't just have images, but we have images from different satellites, or we can match images to other sources of crowdsourced data on the ground. And we can take advantage of concurrent statistics between the various modalities to learn something about how to interpret these images in an unsupervised way. Or we can take advantage of a lot of unlabeled data. As we've seen, we have very limited labeled data, but we have essentially an infinite amount of unlabeled data. And so we can take advantage of the fact that we have spatio-temporal unlabeled data, and we can use that to try to identify features and representations in an unsupervised way. And finally, we can take advantage of some constraints that we might have and prior knowledge. And again, we can use that to reduce the amount of training data that we need in these problems. So one example of different kinds of modalities that we have access to is the fact that although so far I've shown you images of the Earth taken during day, it turns out that satellites also take images of the Earth during night. And nighttime light intensity is a pretty good proxy for economic development. And I can show that to you qualitatively here. This is an image of the Earth in East Asia. And maybe I'll let you think a little bit if you can guess where this is. Any guess of where this might be? Well, you can see that this is actually South Korea, this is North Korea, and the one above is China, right? So you can see the huge difference between the amount of nighttime light intensity that you see in South Korea versus North Korea, which is almost completely dark. So there's clearly some kind of correlation between nighttime light intensity and the level of economic development. So how can we leverage this? Well, the idea is that for every location in the world, we have access to both a daytime image and a nighttime image. And so what we can do is we can try to pose some kind of like self-supervised learning problem where we train a machine learning system to predict, let's say, if I give you these two images, which one is brighter during night. And yeah, go ahead.
There's a question in chat. Isn't using nighttime lighting as a metric, isn't that just contrasting urban versus rural?
That's a great question. It turns out that it's not just that. In fact, if you just use night and light intensity to predict poverty, that doesn't work as many people have done it, but it doesn't work as well. What we're going to do instead is we're going to use that as a proxy. And as I'm going to show you next, we're going to try to teach a neural network to predict night and light intensity. And in order to do that, basically, we are going to force the network to learn how to identify elements that are kind of like related to economic development. So by trying to contrast these two images, we as humans are able to tell that the left one is likely to be more bright at night because we can see cars, we can see a lot of houses, we can see elements that we associate with economic development, with infrastructure quality. While on the right, we see that, okay, there's a lot of trees, barren land, and so we might not expect to see as much night and light intensity. So what we can do is we can generate a huge training data set where we collect a lot of locations, we look at the night and light intensity, and then we ask a neural network to basically predict the night and light intensity from the data image. And by doing so, the hope is that the neural network will basically learn how to identify features that are predictive of night and light intensity. And hopefully this feature then will also be useful for predicting poverty. And indeed, if we kind of like look at the features that the neural network identifies by doing this, we see that this is an example of one of the feature maps that is learned by the network. We see that if we fit in this image on the left and we look at which pixel activates this feature map the most, we overlay the two, we see that kind of like this neuron, this feature is kind of like looking for roads. Another neuron that we might have is kind of like looking for water bodies. And if you do this for a lot of the neurons in the network, we find that, okay, there are, by doing this kind of pre-training, we learn how to identify cars, houses, tall buildings, swimming pools, farmland, and many other such features. So by pre-training the model to predict night and light intensity, we're basically able to learn in an unsupervised way how to identify concepts and features that are hopefully then also predictive for different kinds of, for other indicators that we might like to predict, like poverty, like access to infrastructure quality, and things like that.
So one clarifying question, Stefano. You're predicting a pixel by pixel level of nighttime light intensity, or is it an image level intensity levels that you're predicting? Low, because in the previous slide you had low, medium, high, just three things, and I was not sure whether it was for a pixel by pixel level or.
It's at the image level. So we are basically we're bucketing effectively, because classification ended up working better than regression, although you could have done regression too. More specifically, what we do is, we basically take an image, an area, and then we compute the average intensity for that area. Then we bucket it into classes, and then we essentially cast it as a classification problem where we ask a convolutional neural network to take the image and predict the corresponding night and light intensity.
Yes, a related follow-up question would be to how big, I mean, in order for you to be able to have meaningful estimates of poverty from the things that you learn, you would have to make sure that the area that you're considering inside your image should not be too large. If you're considering the average light time intensity in that area. So how big are these areas generally in the images that you're considering?
Yeah, so the way we typically then make predictions is, so we never try to make predictions at the household level, because even that data is actually not even available. The only data that we have available in the surveys is basically kind of like averaged at the village level typically. And so the kind of predictions that we make are typically at that level, maybe 1 kilometer by 1 kilometer. That's typically the resolution that we're trying to make predictions at.
Makes sense. Thank you.
Right. So this is one way that you can try to sort of like get around the training data scarcity. You can try to do some sort of pre-training and train a neural network to identify features that are hopefully useful for a lot of other downstream tasks. Another thing that we can do is we can take advantage of crowdsourced data to provide supervision to neural networks. it turns out that a lot of Wikipedia articles are actually geolocated, meaning that they have like a coordinate box on the right-hand side, where basically it would tell you, like the Nelson Mandela Bridge is located at this coordinate. And it turns out that there is a lot of articles that are geolocated. We plotted this fan map is basically showing the distribution of articles in the English Wikipedia that are geolocated. So every dot here corresponds to an article that has a corresponding location. And what's interesting here is that we didn't overlay the shape of the continents here. That automatically arises just because people tend to write articles about things that are next to them or next to where people live. And so you can see that indeed the density of articles is kind of like correlated with population density. And there's not a whole lot of articles in the middle of the ocean, although there are a few. And most of the articles are where the highest population densities are. And the idea is that these articles contain a lot of information about what's going on the ground. And so we can kind of think of the Wikipedia article as being a very detailed label or captioned for corresponding for an image taken at that corresponding location. So for every Wikipedia article that is geolocated, we have a coordinate. So what we can do is we can acquire the corresponding satellite image. And then we generate again sort of like this multimodal data where we combine a daytime image, not with nightlets, but with a Wikipedia article of that location. And the article contains all kinds of information about what's going on the ground. And so one way to kind of force the neural network and train the neural network to interpret satellite images is to ask the neural network to basically predict properties of the article just by looking at the image. And so one way to do that we explored is to basically take the Wikipedia article, find a vector embedding using an existing NLP method to basically embed the text into a vector representation. Then take the corresponding satellite image, embed it into a vector using a convolutional neural network, and then basically train the convolutional neural network to produce a vector embedding that is a visual vector embedding that is similar to the textual one produced by the NLP model. And in some sense, we're kind of like trying to train the convolutional neural network to extract useful information from the image that corresponds to the textual information in the Wikipedia article. And again, this is a task for which we have an extremely large amount of data because we have a lot of Wikipedia articles. And the hope is that by doing this kind of pre-training, the network will learn to identify, again, useful features that can then be transferred for different tasks. And indeed, we found that if you then pre-train a network this way using the Wikipedia data, and then you use it to, let's say, on this benchmark data set called functional map of the world, where the goal is to kind of like identify different kinds of infrastructure elements, this can give you a huge performance boost compared to pre-training on something like ImageNet, which is completely different from the kind of images you see when you try to interpret satellite images. Another thing that we can do is to use unsupervised learning techniques. This is something that has worked quite well in natural language processing. The kind of distributional hypothesis behind things like word2vec and similar methods is this idea that if two words appear in similar contexts, then they probably have similar meanings. And so we can apply something similar to geospatial data. The idea is that if things are closer to each other in space, then they probably have a more similar meaning. And so we can kind of like leverage this intuition to develop unsupervised or self-supervised learning methods to try to leverage unlabeled data to come up with good representations automatically. And so intuitively, you can think of setting up a task where, let's say, we have a satellite image, we remove a patch, and then we ask a neural network to try to predict what is the patch that you should put there to fill the gap, right? So this is similar to, if you're familiar with NLP models, this is kind of like similar to try to train a neural network to predict missing words in a sentence, which is kind of like a standard pre-training methodology that is kind of state of the art in a lot of NLP settings. And we can do a similar things for images at the level of patches. And by doing this, we're basically encouraging the model to find a representation of the images such that images that are close in space end up having a similar representation in this feature embedding that hopefully will be useful for downstream tasks. Another thing that we can do is we can kind of take advantage of recent contrastive learning methods. They're the idea that has been just kind of like giving state-of-the-art results in a lot of computer vision applications are things like MoCo or SimClear, where the idea is that if we have, we can take two images, and then if we extract patches from these two images, then the representation that we obtain from two patches that are coming from the same image should be closer than the representation of than patches that we get from two different images. So these two patches from the same image should be closer to each other than these two patches that come from different images. So we can kind of adapt these sort of techniques to spatio-temporal data and satellite images, taking advantage of the fact that we not only have spatial information, but we also have temporal information. So we can get multiple images for over time for the same location, and we can use that to essentially construct pairs in existing contrastive learning methods. And we can get significant improvements when we apply contrastive learning, self-supervised contrastive learning methods to satellite images. Now, once we do that, we use one of these techniques to sort of like pre-train the networks. Then what we can do is we can finally go back to the problem of basically predicting survey data from space. The idea is that we're going to have a few locations for which we have survey data. These are villages that have been surveyed by, let's say, the World Bank or some kind of statistics office of a country. And what we can do is for each location, we can acquire the corresponding satellite image. And we can use one of these techniques to basically extract visual features, either by pre-training the network on predicting night lights or Wikipedia articles, or even just in a self-supervised way. And then what we can do is we can essentially train a separate model or fine-tune the model to try to predict indicators from the survey data, like let's say poverty rates or population density or access to infrastructure quality. And we can try to predict it using these rich visual features. And indeed, we've shown that because these features are useful, these features kind of like, are capturing things like, are there houses there? How good are the roads? And things like that, we can actually do a pretty good job of predicting economic indicators. This is an example from an early paper where we were trying to predict essentially wealth levels across different locations in Uganda. Every dot here corresponds to a location that was surveyed by the World Bank. So there is a ground truth asset score, just kind of like a measure of wealth. It's kind of like looking at the kind of assets households hold in that area. And we can try to predict that from space just using satellite images. And that's what we plot on the y-axis. So ideally, if the model was perfect, you would see all these dots landing on the diagonal, meaning that the predictions that we get are exactly the same as the actual asset wealth measured on the ground. And you can see the model is not perfect, but it's actually doing a pretty good job. We get R-squares of around 0.6, 0.7, which means that we can basically capture over 70% of the variation that exists on the ground just by looking at satellite images, which again are sort of like available everywhere. They're cheap, they're frequently updated, which makes this procedure a lot more scalable and inexpensive compared to traditional survey methods. Another thing that we can do is we can also take advantage of the unlabeled data in a semi-supervised learning fashion. The idea is that although we have very few locations for which we have survey data available, there's a lot of locations for which we have the corresponding image, or we don't have the corresponding ground truth, let's say asset wealth value. So one thing that we can do is we can take advantage of ideas that have been used before in the semi-supervised learning community. And to give you the intuition, why it might be helpful to have access to unlabeled data as you try to learn a classifier. Consider this setting where we're trying to learn a classifier that is distinguishing between points belonging to the blue class versus the red class. And if we are in a regime where we have very little training data, and we only have, let's say, 6 labeled data points, there is many decision boundaries that you could come up with that would provide excellent classification performance, right? So you might decide that given what given these 6 data points, the decision boundary that you decide to pick is, let's say, this one. However, if now I give you a bunch of unlabeled data for the same problem, so I give you a bunch of data points for which I don't have the corresponding label, so I'm showing them in gray, then you might say, well, wait a minute, maybe that decision boundary that I come up with before is not the right one. Maybe I'd prefer to kind of shift the decision boundary this way, because it feels like probably all these points actually belong to the red class and all these points actually belong to the blue class. And so the kind of like the intuitive idea is that we are trying to shift the decision boundary to reduce the uncertainty of the predictions that we make at unlabeled data points. Right? So if the decision boundary is here, then there's going to be some unlabeled data points for which we're going to make a fairly uncertain prediction, which is going to be right through the decision boundary. While if we move the decision boundary here, then we're going to make relatively confident predictions at the unlabeled data points. Even though we don't know the label, we're going to make a more confident prediction because they're going to be further away from the decision boundary. And so that's a principle that has been used before, this semi-supervised classification by entropy minimization. And the idea is that we can kind of take advantage of this also in a regression setting. Again, we have these locations for which we're making predictions using images, extracting features, and then doing some kind of regression model. If the regression model is one that produces uncertainty estimates, let's say like a Gaussian process, then what happens is that our model will not only produce a prediction for an unlabeled data point, which is shown by this black line here, but it will also give us a sense of how uncertain the model is in the prediction that it's making. And so maybe for this, which is kind of like shown by this uncertainty envelope here. So for some points, intuitively points that are similar to the training data, the model will make more confident predictions. While if the unlabeled data points are far away, they're very different from anything the model has been trained on, then it will tend to make more predictions that are less confident, for which there is more uncertainty. And although we don't have labeled data for these blue points, these locations that were not surveyed in our training data, what the Gaussian process regression layer do is it will produce predictions, and it will produce an estimate of how uncertain these predictions are. And so we can use the same principle as before, and we can try to take advantage of all the unlabeled data and essentially change the training objective to say, well, let's try to fit the labeled data as well as we can. But at the same time, we're going to try to minimize the uncertainty of the predictions at the unlabeled data points. So intuitively, we're basically going to change the weights of the neural networks and the Gaussian, the hyperparameters of the Gaussian process, so that we're going to try to change the representation of the unlabeled data points so that the uncertainty is reduced, so that the unlabeled data points become more similar to the labeled ones. Intuitively, we're sort of like trying to identify features such that that are not only useful for doing regression on the labeled data points, the red ones, but at the same time, they're also useful they also make the unlabeled data points similar to the ones for which we have labels. And by doing this, since maybe I don't have a whole lot of time, but again, this is a very useful technique that can be used across a range of different regression problems, and in particular, it significantly reduced the error rates on this poverty prediction task. Now, once we have one of these models, again, the exciting thing is that We can use them to make predictions over large geographies, because after the model has been trained, the only input that we need are satellite images, which are available everywhere and relatively inexpensive. In particular, we can even try to make predictions in countries for which we don't have any survey data at all. Even for countries for which we have survey data, we can make predictions at locations that were not surveyed before. And so, we can kind of like fill in the gaps, and we can go from 100, maybe a few thousand villages surveyed, and we can make predictions everywhere for every single village, every single location in the country. And so we did that. We actually did scale up this approach, and we produced economic indicators for the whole African continent. So for every country now, you can basically see what is the, let's say, asset wealth at the level of states, or you can zoom in at the level of countries. You can zoom in at the level of individual villages. You can see how we can do this over time, because the images are updated relatively frequently. You kind of like apply this approach over, as soon as new images become available, we can basically update our predictions. And we can use this to track changes. Here is an example of this, like where we're looking at West Africa, Ghana, and Ivory Coast. And you can see like the striking difference between these two countries. If you look at how asset wealth has changed from 2003 to 2018, you see that the model is picking up these huge differences between these two countries, where one is actually kind of like blue, there's almost no growth, where the other one is growing rapidly. Ghana here on the right is all red, is growing a lot. And indeed, even though the model didn't know anything about the geography, didn't know about, oh, this is Ghana, this is Ivory Coast, it's actually picking up the fact that there was a big civil war in one country, while the other one was experiencing huge levels of economic growth. So that's exciting. We've done this over a lot of different countries and villages. Overall, the accuracy is pretty good. At the village level, we get R-squares of about 0.6, 0.7. Again, so like the mean R-square is shown here. Every country is basically color-coded by the R-square that we get in that country. And you can see that, it's always larger than 0.5. It can go up all the way up to 0.8, 0.85 even. So these estimates are pretty accurate. If you're willing to go at the district level, so basically producing estimates with less spatial granularity, the R-squares become even better. Maybe 0.75, 0.85, things like that. And we think that they're basically pretty close to the accuracy of that we actually have from the surveys. The surveys themselves are not perfect. They're based on interviews, people forget, there are mistakes in the recordings. So there is actually noise even in what we consider ground truth data, the one that we've used to train the model. And in fact, the correlation between our predictions and the survey data that we use to train the model are actually pretty close to the kind of correlations you would get if you were to take two surveys that were done in the same country, and you try to see, okay, here's a survey done by the World Bank, here's a survey done by the local government, how well do those two match up? The correlations that you get are going to be pretty close to the correlations that you get if you were to match up our satellite-based estimates to the surveys. So if you look census versus satellites, the R-square is 0.7. If you take a census versus a survey, you get 0.8, 0.7, something like that. So it's pretty close to kind of like the accuracy that we think to sort of like the amount of noise that is anyways in the labels that we've used for training the model. And so we're pretty confident that these predictions are actually quite good, and we can start using them to inform policy, to help to understand how things are changing on the ground, whether interventions are working or not, and other kinds of exciting applications that would not have been possible with the kind of very limited data that's typically available on the ground. One further challenge that I'll mention is that this is a really expensive kind of computation. I mean, it's cheaper than sending people on the ground, but if you want to produce this kind of maps for a whole continent, it involves a lot of computation and a lot of images. even just producing a map for a country like Kenya, typically it would involve something like in the order of 10 billion pixels in medium resolution, several trillion pixels if you want to process images in high resolution. So it's a huge computational expense to process all these images. And so we've been looking at ways to make this pipeline more efficient, more adaptive. And one way to do that is to essentially develop adaptive data acquisition and data processing pipelines based on reinforcement learning. So the idea is that processing medium resolution images is relatively cheap, relatively inexpensive. And a medium resolution image of a town might look something like this. And then you can ask yourself, would you rather, if you had to pick a high resolution image, would you rather pick it down here, or would you rather kind of like zoom in up there where it seems like there are buildings and people live? And so the idea is that we can perhaps train an agent, a machine learning model, to essentially figure out when and where to zoom in order to maximize accuracy in the final prediction, while minimizing the kind of compute and cost that is involved when we need to acquire multiple high resolution images and we have to process them. So we basically train our reinforcement. You can think of this as a reinforcement learning problem where there is a cost associated with acquiring high resolution images. And then there is a reward that is associated with making correct predictions. And you can train a system to basically automatically figure out when and where to zoom. And so it might decide, okay, this is a useful patch. So for this patch, I'm going to actually acquire the high resolution image. And then I'm going to do object detection. And then I'm going to use these object detections to come up with my estimates for economic indicators. And by doing this, we can actually scale up to very large geographies. There is a lot of locations for which you don't need to acquire high resolution images because nobody lives there. Even for locations where people live, you can basically sparsely acquire high resolution images, and with very small drops in accuracy, you can significantly reduce the costs associated with acquiring the images and processing. Now, I guess I'm kind of almost running out of time, but we've applied these kind of ideas not just to economic indicators, but also indicators related to food security. We've been able to predict from space basically how productive fields are in terms of, say, soybean, maize, key staple crops in developing countries, also in the US. So we are able to basically produce very similar maps where for a whole country, we can figure out how productive are cornfields in these parts of Kenya. And you can zoom in all the way at district levels. You can zoom in all the way to individual fields. So this map is basically showing different fields in this part of Kenya. And where for each individual field, we're basically able to predict, is this field productive as shown in red, or not so productive as shown in blue? How much maize will be produced in that field for that particular year? And we can do this again for huge geographies, for a whole country at the level of individual fields, and we can do it pretty accurately. So again, this is a game changer if you think about the way this kind of data, which is really helpful if you're thinking about food security, about hunger, about how people are adapting to climate change. We are able to provide very local, very accurate data over huge geographies in a very inexpensive way, just by combining machine learning with satellite images. We can do that. We can predict quality of infrastructure. We can look at population density and many other things that are visible from space. You can look up some of the papers if you're interested. We can also look at, we started recently looking into not just images from space, but actually things like essentially Street View images. I mean, Google Street View is not actually available everywhere, but there is an alternative called Mapillary, which is actually crowdsourced. So it has like hundreds of millions of images collected along roads all over the world. The images might look like this. And again, these images contain a lot of information about what's going on the ground. And we've recently shown, this was in India, that we can basically take all these images, process them, do object detection, and then use these objects that we see to come up with pretty accurate estimates of poverty, wealth, population density, and even indicators that are related to malnutrition and hunger, like BMI, stunting, wasting, and things like that. So I think this is pretty much, I'm out of time. So it's a good time to stop, but hopefully this give you an idea of the kind of things we're doing at Stanford in this space. The overall vision is that, we're facing some really important problems, like the ones you've seen, the SDGs, problems like ending poverty, hunger, climate change. I do think that we need more people these are the big problems that our society is facing today. These are the problems that I want to work on. And I do think that there are ways to leverage all the advances that we've seen in AI and ML to come up with more data-driven, more quantitative solutions to these problems. And this is, of course, joint work with a lot of students and postdocs. And I'm happy to take questions on the various things I talked about today. And thank you for listening.
Thank you, Stefano. Thank you for the wonderful talk. We have time for questions. We have about 5 minutes. Does anybody have any questions? I guess I can get started. So one question that I had, Stefano, is about the prediction of poverty using nighttime light intensities. What would you, so I have two corner cases, if you will, that I thought, I thought of, and I was wondering if they are actually a problem, or are these things too rare an occurrence inside the data that you have? So in many parts of the world, there are regions which consist of very, very exploited populations. So people who are extremely poor, the government doesn't do anything for them. A case in point is a region in India called Chhattisgarh. There are lots and lots of poor people, tribal villages, farmers, etc. And what the government does is they bring in lots of industrialists. They give or lease off land there to industrialists at very low rates. So you might see a lot of nighttime activity because of the industry. So it's an industrial zone, right? But the people who are living here are the poor, some of the poorest in India, for example. So is that too rare an occurrence inside the data that you have, or?
That's a good question. Of course, these are statistical models, so they will potentially make mistakes. One thing that I would like to point out is that we're not predicting directly from night lights, but we use night lights as a pre-training, just as a way to identify features like that are then trained directly to predict, let's say, poverty or other kind of indicators. Mm-hmm. So these features are not perfect. We do make mistakes. As you said, there are situations where, especially in urban areas, it's just by looking from space, you basically cannot tell what's going on the ground because you cannot see inside people's homes. And so, the model does make mistakes, but if you look at the R squares, which are always out of sample, so you train on your training set and you evaluate on test data that you haven't seen before, the R squares are pretty decent. So you can explain it, the R square is 0.7, 0.75, 0.8 maybe. So we can't rule out that there's going to be mistakes. There's definitely going to be some, but on average, it seems to work reasonably well. And so, but yeah, there are limitations to what you can do. So I don't think we will ever be able to completely get rid of survey data collection on the ground, but the hope is that we can complement it, because then we can maybe combine the two, and we can, instead of just getting data on a few hundred villages or getting a census every 10 years, we can kind of like interpolate and produce a much more fine detailed picture of the situation on the ground.
So just so I understand that, and that your answer definitely makes sense. So just so that I understand your model properly, once you get the feature maps that you learn from that initial prediction problem, you are in addition also using survey data from these
Yeah,
areas to finally predict the economic development heat maps that you're generating. Okay.
Yeah. So we always need some survey data. Ideally, some survey data from the country. You're gonna then test your modeling. That's the best case scenario. Sometimes like places like Somalia, there's no training data available at all. So the best we can do is we can basically train on survey data from different countries and hope that the model will generalize in this new country, but we don't have any ground truth to evaluate the predictions. So what we do is we instead try to leave one country out cross-validation, where let's say we pretend we don't have data for a country, we train on neighboring countries and then test how well we would do. And so we have a sense that the model does generalize reasonably well across borders. So we're pretty confident that even the predictions we make in places like Somalia are not too bad, but we don't have any ground truth data to actually evaluate those predictions. In countries for which we do have survey data, then we can rigorously evaluate the predictions. We have held out data. We can try to make predictions in villages for which we do have ground truth data that we haven't seen during training, and we can check how well we do. And the R-squares that we reported seem to indicate that we can actually come up with pretty accurate estimates.
And I wonder if you thought about using crowdsourced data. We work with surveying is essentially one way of crowdsourcing, right? But so we are working with an NGO called Plant Village here I don't know if there's a representative from Plant Village among the attendees. Maybe there isn't, but basically what they've done is they were trying to look at this locust problem in East Africa. And what they've done is they've developed a smartphone application with the United Nations FAO, which they've given to farmers everywhere in East Africa, who then, in addition to the data, in addition to looking at remote sense data, they also have this data where, farmers, anytime they see a locust swarm in front of them, they can use their phone to record that, which might or might not be a good idea. At least it's something to consider for this domain as well.
Yeah, in fact, one of my collaborators in the Sustain lab, like this kind of like sustainability and artificial intelligence lab, I know he was looking into a similar kind of idea, but in India, like there is a startup that is kind of providing advice to farmers about, I think, pests and best sort of like practices. And
is it the same startup? Maybe, because they operate in India as well. So
it's the same. And they take photos and then you send photos of the crops and then they give you some advice on what you should do. And so they were actually trying to use that data as kind of like weak labels or like possibly noisy labels to try to do crop type mapping and crop type segmentation in India. I think one challenge was that the locations of the labels, they didn't match up very well with the actual. I think connectivity is bad, or sometimes like the location of the image they tended to be not very consistent to where they should have been. I think either because of noise in the GPS or because there is no, I guess, internet connectivity in the farm. So they have to go back to wherever they have internet connectivity to send the data back. And so there's some kind of mismatch in the locations. But yeah, they were able to do some interesting stuff there, because the advantage, is that they are noisy, but you can get a lot more compared to, the kind of traditional survey data that people use.
So I have one final question. I know I haven't given others a chance to answer, but this is something that I've always struggled with in these domains, because we face this in our work as well. How do in your work, how do you evaluate how important it is to increase the R squared, for example, from 0.65 to 0.67? What does that translate to in terms of some improved provision of services that you want to achieve, or policy planning? Is there anything, has there been any thinking along these lines that how good is good enough, basically?
Yeah, that's a very good question, and we don't necessarily know the answer, and we don't even know how much noise there is in the ground truth data, so we don't even know what's possible. What we did is in the 2020 Nature paper that talks about how we scaled it up to the whole Africa. We did this little exercise, but it wasn't like a simulated exercise, but kind of like trying to figure out how much better would aid program how much better would the targeting of an aid program become if you were to use these kind of predictions as opposed to what was available before.
Mm-hmm.
You kind of like try to simulate, if you're giving aid based on these estimates, how much more accurate would it get?
Interesting. Okay.
And so, but it's a good point, right? And then you can kind of translate that R-square into, okay, then we're going to be able to reach the right population a little bit better. And so you kind of like translate it to how would policymakers eventually end up using these predictions in the real world.
Interesting. I'll ask you for pointers if it's been published. Okay. So if does anybody else have any questions? Anyone? Okay, I guess in that case, what time are we at? We're out of time. Thank you so much for attending. Thank you so much, Stefano, for giving this wonderful talk. I certainly enjoyed it, and I'm sure the others did it as well. And yeah, thank you, everybody.
Yeah.
Thank you. Bye-bye.
Bye-bye.